Alright, so in this video what I'm going to do is I'm going to review the section B, the multiple choice, for a specimen paper 2, but this is the second specimen paper, which isn't generally available online, but some of you might have had a look at for a mock exam or something. So first off, we've got an ice cube of mass 0.10 kilograms at a temperature of 0 degrees, and it's dropped into 0.1 kilograms of water, which is at 15 degrees. What is the maximum estimated temperature change of the contents of the cup? And I'm guessing we're going to assume it's insulated from the surroundings. So, first of all, we can eliminate option D straight away. There's no way it's going to stay at the same temperature. Some energy's got to go to the ice to melt it, because essentially the system's going to try and reach a uniform temperature at the end, and it's going to be somewhere between 0 and 15, so it can't be 15. So I guess the way to think about this is we've got to melt the ice, so we're going to have to calculate somehow the energy to melt the ice, and we have this equation, E equals ml, to do that. So mass of ice is 0.01, that's how much ice we have, and we have the latent heat of fusion, which takes this value, so we can calculate how much energy that takes, and that comes out as 3,400 joules just to melt the ice and keep it at 0 degrees. So that energy has got to come from the water that surrounds it. So let's calculate the change in temperature of the water to melt the ice. So we know how much energy there is. We also know how much the mass of water is, 0.1, and we know the specific heat capacity of water is 4,200. So let's calculate the temperature change of the water, and that's 8.1 degrees Kelvin there. So that's the temperature. So the temperature of the water afterwards is going to be 15 minus that. So it's going to be 6.9 Kelvin. And that's when the ice is melted. So the ice is now at 0 degrees, but it's all water. And the water is now at 6.9 degrees Kelvin. So if we analyse what we've got here, so we've already found the water changes temperature about this, and it's only going to change by more because it's going to approach the temperature of the ice. So we can eliminate option A at this point because we've already found a temperature change bigger than that. So it's starting to look like it's going to be more towards B than C, but let's see if we can figure it out. So now when it reaches thermal equilibrium, they're going to be at the same temperature as each other. So let's have a look at, so to raise the temperature of the ice, so I'm just going to call the final temperature TF, and the ice is what was ice is now at 0, and we've got 0.01 of it. That's the energy gained by the ice, what used to be the ice, and this is going to be the energy lost by the water. So what we can do is we can solve that. So we get if we divide both sides by 0.01 to start with, so we end up with TF is equal to 10 times 6.9, 69, and then what we can do is we can solve this to find the final temperature, which is 6.2 Kelvin. So the ice has changed by 6.2, but we're after the maximum change. So the maximum change in temperature is going to be that of the water, which is going to be 15 minus that answer is 8.7 Kelvin there. So B is the correct answer for this one. So just to recap what I've done there. So first I calculated the energy to melt the ice. So now we've got, and then we worked out what the temperature of the water would be once we've melted all of the ice. So this is why we put ice in drinks. It will cool down the rest of the stuff in order to melt the ice. Once we've got that, what I've done is I've said, well, they're going to reach the same temperature when they're in thermal equilibrium. So the amount of energy gained by the water that used to be ice is equal to the amount of energy lost by the water that was always there. And I found what the thermal equilibrium temperature is. I would have had a C, but it would be the same on both sides, so I've cancelled it. And then I've worked out the temperature change of the water from 15 degrees to 6.2, and it's 8.7 Kelvin there. Judging by the masses, I could have gone straight for answer B without actually calculating this, because the mass of the water is much bigger, so the temperature change of the water is going to be quite a lot smaller. So we knew it would end up close to the 6.9 value, so we would have known it wouldn't be 13.5, but I just wanted to show you that fully so you get to the answer. Okay, so that's that one there. So moving on to the next question. So we've got two gases that are at the same pressure, and we've got one at a certain temperature, 280 and Kelvin, and it has 10 to 20 molecules per unit volume, and the temperature of Q is 350. So when it says unit volume, what we can do is we can put in V equals 1, and we're going to use the ideal gas equation like this. Okay, so we're using a unit volume, so we can make the volume 1. And we've got the two pressures are the same, so P1 is equal to P2, or PP is equal to PQ there. So what we can do is go N1 RT1. Whoa, that went a bit crazy. T1 is equal to N2 RT2, and we want to know the number of molecules, so we want to know N2. Because we put V equals 1, it's automatically going to be per unit volume, so it's going to be N1 T1 over T2. And then we had 10 to the 20 molecules when we have 1 meter cubed, if you like, or 1 unit of volume. Initial temperature was 280, and the new temperature is 350. Ooh, that's exciting. And then once we calculate that, let's do that now. 280 divided by 350 times 10 to the 20. That comes out as 8 times 10 to the 19 molecules per unit volume, which is the same as 0.8 times 10 to the 20. So it's answer C. So question 8, which of these is not used as an assumption when deriving this equation, which is the kinetic theory derivation essentially? So A says the molecules suffer negligible change in momentum on collisions with the walls of the container. That's absolutely not true. We assume those collisions are elastic, which means they suffer a change in momentum of minus 2 MV. So that's absolute rubbish. So that is the correct answer because it's not. We do definitely assume the forces are negligible as part. We assume no intermolecular forces. The duration of a collision is negligible compared with the time between collisions. Yes, we do assume that because we only use when we're using the time in the equation, we use the time to go between the collisions. The volume of the molecule is negligible compared to the volume of the gas. Again, yes, we do use that there as part of the derivation. Okay, so 1 mole of gas occupies a volume V at pressure P and a Celsius temperature of theta. Graphs A to D show variation of PV with theta. X is for 1 mole of nitrogen and Y is for 1 mole of oxygen. And we've got these two masses. Which graph is correct? Okay, so if the temperature is in Celsius, remember our equation PV is equal to nRT in Kelvin, so that's equal to nRT in Celsius plus nr times by 273.15 there. So now that gives us temperature in Celsius. So let's put a subscript K there. Okay, so we can see that this is a linear type graph with a y-intercept. So we can see straight away it's not going to be A, because that suggests it's directly proportional, and the others we can't get. Okay, so the gradient of our line should be n times r, where n is the number of moles and r is a constant. Okay, so we've got 1 mole of each, so we've got n equals 1 in both cases. So in theory, these two graphs should end up with exactly the same gradient as each other because n is the same. So the answer is going to be D. Okay, so we've got the distance between the Earth and the Moon, and we've got their masses, and we want to know where a spacecraft can be for the it to experience no force. So if it's going to experience no force, essentially what we can do is equate the two force expressions like this, and we've got this one m over r2 squared. And we can cancel out things that are the same on both sides, and we end up with this one here. So I usually do it in this way around. So the ratio of the masses is equal to the ratio of the distances squared. So essentially, if we set the Earth as m1, Earth has a much bigger mass, therefore the distance of the neutral point from is going to be bigger as well. So if m1 is bigger than m2, r1 has to be bigger than r2. So essentially, it must be much closer to the Moon than it is to the Earth. So we can already eliminate A and B because those are very close to the Earth, because you can see they're a power of 10 down. 3.8 is exactly at the Moon. Well, it's not going to be there, so we can get to the fact that the answer is C here without actually doing any calculations. And if you do the calculations, it would take you a very long time. So you need to be a bit smarter with a question like this. Okay, so an electron on the surface of the Earth is placed in electric field strength of 5,000 newtons per coulomb. What is the ratio of the electric force to the gravitational force? So you should know the electric force is going to be much, much bigger than the gravitational force. In your ranking of forces, gravity is dead bottom and is really weak. So we can eliminate A and B straight away. So essentially, it's which order of magnitude is going to be C, or is it going to be D? So if we can work out the force, the electrical force is going to be the field strength times the charge, and so that's going to be 5,000, and it's an electron, so 1.6 times 10 to the minus 19. So let's do that calculation. 1.6 times 10 to the minus 19 times 5,000 is 8 times 10 to the minus 16. The force of gravity is going to be Gm m over r squared. So we're going to do 6.67 times 10 to the minus 11, that's G, times 6 times 10 to the 24, that's the mass of the Earth, times 9.11 times 10 to the power of minus 31, that's the mass of an electron, divided by 6.37 times 10 to the 6 squared, and you get 9 times 10 to the minus 30. So we can see going between here and here, we have a power of 10 change of about 14. So we can see the answer is going to be D there. I haven't been too precise. Okay, so The radius of a planet is r. The gravitational potential at the surface of the planet due to its mass is minus 4,000 joules per kilogram. What is the gravitational potential at a distance of 2r from the center of mass? So you should know that potential varies with an inversely proportional relationship to distance. So doubling the distance should halve the potential. So that's going to give you an answer of minus 2,000. Satellites X and Y orbit the Earth at distances of r and 4r respectively. Which statement is incorrect? So the speed of Y is greater than the speed of X. That is not going to be true, because if we think about it, to be a satellite, what you need to do is essentially equate the gravitational force with centripetal force squared over r. So we can cancel one of the r's, but we can see the bigger r is, for the same mass, the smaller v would have to be. So actually the answer is A. But let's go through and check the others too. It's always worth having a look at. Time period of Y is greater than X. Well, yeah, it's traveling much slower and it travels a much larger distance, so that makes sense. Potential energy of Y is greater than the potential energy of X. That's true. They're both negative, but it will increase to 0 the further away you get, so that's true. The gravitational force acting on Y is less than that of X. Yes, it's further away and the force decreases with distance. Okay, so an alpha particle makes a head-on collision with a gold nucleus containing 79 protons. The distance of closest approach of an alpha particle is 4 times 10 to the minus 14. What electrostatic force acts on the gold nucleus when it's at this separation? So we're going to use Coulomb's law of charge. So we're going to use Q over 4 pi E0 r squared. So we're going to do 79 times 2, because an alpha particle has a charge of 2, times by 1.6 times 10 to the minus 19 squared, because there's 2 times the charge of electron, divided that by 4 times pi times 8.85 times 10 to the minus 12, times by 4 times 10 to the minus 14 squared. And we come up with an answer of 22.73, so that's going to be 23 newtons. So actually, considering these are between subatomic particles, that is a massive force that is acting between them. So we've got an electron moving at constant speed and it enters a uniform electric field at right angles to the direction of the field. What's true about the force acting on the electron? It's at right angles to the direction of the field. No, that's wrong. So if we sketch it, so your field is going, let's say, that way, and that was positive, and that one's negative, and you've got an electron going across that way. So the electron is going to experience a force upwards because it's going to be attracted to the positive plate. So that is clearly parallel to the field, so that's wrong. In the opposite direction to the field, well, we can see that from the diagram, that's true, so that's the correct one, but let's check the others anyway. Because the electrons continue in the same direction with the speed increasing steadily. No, it doesn't. It would make the direction, it would travel in a parabolic path. Because the electrons go in the same direction, already wrong, so let's not even finish with that. Okay, so two fixed parallel metal plates P and Q are at constant electrical potentials of 100 volts and 70 volts respectively. A proton travelling from P to Q experiences a force due to the electric field between P and Q and a change in potential energy of delta EP. Which line A to D gives the direction of F and the value of delta EP? So protons are positive, so it's going to be experience a force towards the least positive thing. So it's going to experience a force from P to Q, or in this case towards Q there. So we can already eliminate the answers which suggest it would be towards P. Okay. So over here its potential energy would be the most positive. Over here, it would be the least positive. So it's going to experience a decrease in potential energy as it goes across. So that's going to mean it's going to be option C. Blimey, there's a lot of news today. Anyway, that's that one. Initially, a capacitor stores 600 microcoulombs of charge. When it loses half of this charge, the potential difference across it decreases by 50 volts. What is the capacitance of the capacitor? So, if you halve the charge, you have halved the potential difference. So essentially, the potential difference must have gone by 100 volts to 50 volts because it has to have halved, and halving has to be the same as decreasing by 50. So C is Q over V. So its charge was 600 times 10 to the minus 6, because it's in microcoulombs, and that's divided by 100, so that's 600 times 10 to the minus 8, or 6 times 10 to the minus 6, so that's going to be option C. Okay, so the separation of plates of an isolated charged parallel plate capacitor is increased. What also increases there? So the capacitance increases. No, that's not going to work. So you should know this equation to calculate capacitance. E0 ER over D. So we know that increasing this plate separation actually decreases capacitance. So that's wrong. The charge on the plates is increased. Well, it's isolated, so it's not connected in a circuit, so you can't change the charge on it. You're stuck with whatever you had. The strength of the electric field between the plates. Well, if you've got the same charge, we're going to end up with the same field strength because we haven't actually changed the charge causing the field, so how can we change the field strength? So then, look, we're left with D. The potential difference between the plates increases. That is absolutely true. If we keep charge the same and we decrease the capacitance, we can see that the potential difference has to increase. So that one is correct. The initial charge stored by a capacitor of capacitance 0.5 microfarad is 2 microcoulombs. The capacitor then discharged through a resistor. How much energy is stored by the capacitor after a time equal to 1 time constant? So after 1 time constant, both the potential difference and the current will have decreased to 37% of their initial one. So the charge on it at this time is going to be 0.37 times by 10 to the minus 6. So get its micro times by 2, obviously because it's 2 microcoulombs. So let's calculate what the charge is. And we get 7.4 times 10 to the minus 7 coulombs. So energy we can calculate using half Q squared over C. Let's do that. So we square our answer, divide it by 0.5 times 10 to the minus 6. Divided by 2, and we get 5.476 times 10. So it's basically 5.5 times 10 to the minus 7. So we can see that is approximately answer B there. Okay, so a 500 microfarad capacitor is charged to a PD of 10 volts, is then discharged through a 100 kilo ohm resistor. What is the time taken for the potential difference to fall from 10 to 5? Okay, so for a capacitor circuit, the time to halve is 0.69 times the time constant So and time constant is RC, so it's going to be 0.69 times by 100 kiloohms, so times 10 to the 3, and then times by our capacitance, so 500 times 10 to the minus 6. And when we calculate that, that comes out as 34.5 seconds. So that's going to be answer A is the closest to that. So a horizontal copper wire of mass 4 times 10 to the minus 3, so 4 grams, and length 18 millimeters is placed perpendicular to a magnetic field of flux density 0.16 Tesla. The magnetic force acting on the wire supports the weight of the wire, so they're in equilibrium. How many electrons are passing a point in the wire each second? So the force must be equal to the weight force, which is 4 times 10 to the minus 3 times by 9.81, because we want the weight force. So let's calculate that first of all. That comes out as 0.04 approximately. I'm going to keep them rounded. So we know now we can calculate the force on one electron. By doing that, so what we're going to do is we know the force is going to be equal to the force on the conductor, which is done by BAL. So we can calculate the current from there by dividing the force we've got, so 0.04 divided by 0.16 divided by 80 and 1000 is 3 amps approximately, or which is 3 coulombs per second. One electron is 1.6 times 10 to the minus 19, so divide that by 1.6 times 10 to the minus 19, and that comes out as 1.9 times 10 to the 19 electrons per second there. So just to explain what I did there, 3 amps is 3 coulombs per second, so 1 electron is 1.6 times 10 to the minus 19, so divided by 3 by 1.6 times 10 to the minus 19 gives you number of electrons per second. Okay, so two charged particles, P1 and P2, follow circular paths as they move at right angles to the same uniform magnetic field. Both particles are travelling at the same speed. The radius of the path travelled by P is twice the radius of the path travelled by P2. The mass of P1 is m and its charge is q. What is the mass of P2 and the charge of P2? So, because they're travelling in a circular path, what we can do is equate the magnetic force to the centripetal force, like this. So we can cancel out the V's. So let's leave that as an expression for R. So that's going to be mv over bq. So it tells you the speed it stays the same, and the field strength is going to be the same. So what we get is that the radius of the path is directly proportional to m over q. So it tells us P1 is twice the radius of P2. So essentially going from P1 to P2, your radius halves. So the fraction m over q needs to be half what it was before. So if we look at the table, line 1 would give you an m over q of double what it was before, so that's not right. Line B would give you m over q of the same, because the 2's would cancel out. Likewise, C, the root 2's would cancel each other out, which by process of elimination leaves you, it must be D, and there you can see that m over q halves there if you double the bottom line, so that works. So a rectangular coil of area A has n turns of wire. The coil is in a uniform magnetic field of flux density B, but it's plane parallel to the field lines at this particular moment in time. Okay, so what we want to do is we're going to rotate it by an angle of 30 degrees about its axis PQ. What are the correct initial value and final value for the magnetic flux linkage? So let's have a look. When it's in this position, if you think about it, at this point you're going to have maximum flux cutting at its original position because as it rotates around, which means the max EMF would be induced, and max EMF is induced when magnetic flux linkage is 0. So that's going to make it one of the option A or option B. And then if we think about the expression for it, so magnetic flux linkage is BAN sine theta, or sometimes sine omega t. So when theta equals 30, sine theta equals half, so we know it's going to be A. And we can also look at it when angle is 0, this whole thing is 0, so again we get the same flow flux linkage. That's another way of thinking about it. In the Rutherford scattering experiment, most alpha particles pass through the 4 undeflected, which is the correct deduction from that. So let's go through. Most of the mass of an atom is within the nucleus. Not really, because when he was doing the experiment, you didn't even know there was a nucleus, so that's not a conclusion from it at all. You don't know anything about where the mass is. The diameter of the nucleus is much less than the diameter of the atom. I would buy that, because the conclusion is essentially that there's mostly empty space, so that makes sense. You can't conclude anything about the charge or the charge overall of the atom from the fact that they're undeflected. The charge we learn from the deflected ones, and the fact the atom was neutral they already knew anyway, so that wasn't from the experiment. Okay, so we're using an oscilloscope to measure an AC waveform, and we've got what looks like a sawtooth wave there, because you can see it looks kind of like teeth. When the input sensitivity is set on 1 volt per division, and the time base is on 10 milliseconds per division, we get this trace. And then the student then changes the input sensitivity to 2 volts per division, and the time base to 20 milliseconds per division, which would be observed while applying the same signal to the input terminal. So if you double the Y gain, what you do is essentially double the range that you can show, or you squash your wave. So we need to look at which of these shows the wave being squashed. That means it's either C or it's D there. So we can eliminate A and B because those aren't showing it being squashed. And if we go from 10 to 20, we can double the amount of time we can show on the screen. So we're going to squash the wave along the x-axis. So we're going to get option D there. That's what squashed it, and you can see twice as many waveforms showing. There's twice as long on the screen. Okay, so beta particles are emitted from a radioactive source in a school laboratory. What is correct for these particles? A strong magnetic field won't deflect them. That's rubbish because they're charged at will and they're traveling at speed. They are absorbed by aluminium. Well, beta radiation is absorbed by aluminium, so that's true. They do not damage human tissue. Well, they're ionizing particles, so they would. Their range is shorter than alpha. Rubbish. That's a very straightforward question there. A radioactive source contains a nuclide which has a half-life of 12 hours. A detector is placed near the source. A detector placed near the source records an average count rate of 180 counts per minute. The average background count rate is 20 counts per minute. What will be the average count rate after 24 hours? So first of all, we need to, if we subtract background, we know that the count rate due to the source is 160. So we take off the 20. After 24 hours, we've had 2 half-lives. So we're going to divide that by 4. And now the source is going to be giving us 40 counts per minute. Adding back in background, that's going to give us a total of 60 counts per minute. So then, which graph shows how the radius of a nucleus varies with nucleon number. So you should know the radius is directly proportional to a to the power of a third. So you can see it's clearly not b, because that would indicate that R and A are directly proportional to each other. To a power of a third is not going to be an increasing graph, so that can't be right. And there's no way that it can end up decreasing, so then it can't be D. So then that leaves you with option C. So it's increasing, but the rate of increase decreases over time. Okay, the power output of a nuclear reactor is provided by nuclear fuel, which decreases its mass at a rate of 4 × 10⁻⁶ kilograms per hour. What is the maximum possible power output of the reactor? Okay, so if the mass is decreasing, we're creating a bigger and bigger mass defect, so we can use this old equation here to work out how much energy we're going to be able to release. So we can put in 4 × 10⁻⁶ times by 3 × 10 to the 8 squared gives you 3.6 × 10 to the 11 joules per hour. And we want joules per second, so divide by 3,600, which is 100 megawatts, or 100 million joules per second there. So that's option C. And the last question, the moderator of some nuclear reactors is made from graphite. What is the principal purpose of graphite? So moderators are there to slow neutrons down, because the neutrons produced by a fission reaction are too fast and they need to be slowed down to thermal neutrons before they can produce fission. So no, moderators are not there to absorb heat. Yes, they're there to decrease the speed of neutrons. Nope, they're not there to absorb radiation. That's why you have shielding. And no, control rods are what prevent it from going critical. So you're going to end up with option B to finish off. So that concludes this video. I hope you found that useful to help clear up any issues you may have had with this paper. If you have any further questions, please do comment and let me know. I'd be happy to answer them for you. If you want a copy of this test, your teacher should have access to it. This is a secured paper, but they should be able to get it for you, so just ask them. And hopefully they won't be too annoyed with me setting them on your case.